sources with the pipes of infinite capacity, or say capacity that is equal to the sum total of capacities of all pipes in the network, so that none of these pipes limits the flow in the network, right? And similarly, if you have several sinks, you can connect them with a super sink, again with the infinite capacity of the corresponding pipes. And so this ensures that neither you will restrict the flow by the capacities of these pipes, nor can the mean cut go across any of these pipes simply because their capacity is too large. So you are guaranteed that mean cut, which you find with 4 Fulkerson algorithm, will not cross any of these pipes with infinite capacity. Okay, so this is very useful to keep in mind. Okay, so our next topic is string matching. So what is string matching? You have one very long string of symbols, and you have another shorter string. So the first one can be, for example, a text, and this can be a single word, and you want to find all occurrences of this word in the text. Or this can be a long strand of DNA, and this is a particular gene, and you want to find all the occurrences of this gene within this strand of DNA. So this is obviously an extremely important problem to consider, right? Now, of course, the trivial way of doing string matching would be simply to start from this end and compare symbol by symbol this string with the initial substring of this one, and if it's not a match, you move one element to the right and you repeat this procedure. But this is obviously, it looks that it's inefficient because, for example, every symbol will be checked as many times as the length of this string is. Say the length is here m, and the length of this one is n, right? Because as you progress through the string, you are going to examine what is the symbol here many times, and we want to avoid that. So the first algorithm that we want to see is famous Raben Karp algorithm, which kind of shows in a very clever way the power of recursion. So what is the idea? How do we speed up string matching algorithm? Well, the idea is, so say that the collection, our alphabet, has the following symbols: sigma 0, sigma 1, up to sigma, say, d minus 1. We have d many symbols, right? So cardinality of sigma is d, okay? So now what we can do is we can simply consider a function f that maps symbol sigma I into number I, right? So simply ith symbol is mapped into just I. So in this way, the symbols actually become numbers. Okay? And say our shorter string y, this is our string x, if it has m symbols, then so say y looks like this. It's S1, S2, all the way to Sm. Right? Well, then we have naturally corresponding a string of numbers, which is simply f of S1 all the way up to f of Sm. So simply every symbol will be replaced just by its index, right? Okay, now the idea is that this string of numbers can be seen as a representation of a single number in the base V, right? So now I can simply map this into the following expression. I can have this f of S1 times d to the n minus 1 plus f of S2 d to the n minus 2 plus and so forth, f of Sm times d to the 0, which is just 1, right? So first what we do, we replace every symbol appearing in our sequence with the corresponding, just with its index, right? And now we see this sequence of numbers, so all f of Si is bigger or equal than 0 and smaller or equal than d minus 1. So each of these can be seen as a digit in base D. So this is what this mapping would produce. It would produce a single number, right? And now if you are somewhere, if you want to see whether, say, this would be Si plus 1 all the way to Si plus m. If this string, so this is x from I plus 1 to I plus m, is the same as our string just y, right? What we can do clearly is we can map, we can do exactly the same thing to this string, right? So again, we will map the string x I plus 1, x I plus 2, and so forth, x I plus m. You will map it first into the string f of x I plus 1, f of x I plus 2, all the way to f of x I plus m, right? Simply replacing every symbol with its index, right? And then one step further, we can map this into f of x I plus 1, right, times d to the m minus 1 plus f of x I plus 2 d to the m minus 2 plus all the way at the very end we just have f of x, you just have f of x I plus m. Okay, so this is, so let's call this number this is, okay, so because this sequence is fixed, we are searching for this sequence in the longer sequence. This is fixed, and say this is some value p, and let's call this number here, let's call it pi, okay? So what do p and pi satisfy in case we have a match? If they are the same string, what's the relationship between p and pi? They are equal, right? Now if we had a computer with huge registers, examining whether two numbers are equal is just a single operation, right? But this is not realistic, because usually this string y will be so long that this number simply will not fit in a register, right? So it won't be. So essentially, what this would do if you had a computer with gigantic registers, this would replace matching one by one of the symbols of y with the symbols inside x, with a single operation of just testing whether the two numbers are equal, right? So many comparisons are replaced with a single comparison if, of course, this number and that number could sit in a single register, and each of them in a register, and simply compare the values of the register. But obviously this is not realistic, so the way to handle this problem is that we would use modular arithmetic. But before, okay, let me see, shall I first introduce, yeah, why not, I should introduce first the modular. Okay, so the idea now is to replace these numbers essentially with their hash value. So this will be a nice example of a combination of recursion and hashing. So we will now map number p into p mod some prime q. So q is a large but not too large prime. Okay, what do I mean by that? You want your hash table to be as large as possible to reduce the likelihood of collisions, but on the other hand, you want this remainder of p mod q to fit in a register so that you can also do some operations, as we will see in a moment. Okay, so the idea now is to replace p with p mod q and q, pi with pi mod q. Now, but this again looks wasteful because rather than matching symbol by symbol, we would have to compute this quantity, to obtain this quantity, then to compute its mod q to get the remainder of pi mod q, and this looks to be actually more complicated operation than inspecting element by element, because you have to operate on all bits of pi, right, in order to compute pi mod q. So this is where recursion comes into the play, because rather than computing the hash value of this guy for every shift separately, this hash value, the hash value of this guy can be computed very efficiently from the hash value of the first sequence, of the previous sequence. So what is the idea here? You see, if I move now from here to the next possible occurrence of my string y, so this will be si plus 2 all the way to si plus m plus 1. The idea is now that the hash value of this sequence will be efficiently computed from the hash value of the previous sequence. And this is where the real speed up comes from. So what do you think? How shall we obtain this value? Namely, how to obtain the value of pi mod q? So idea, compute pi mod q recursively from pi minus 1 mod q. How would you do that? So let's see what we have. First sequence is looks like this. Here it is actually. It's written here. The first number. So the first number. How shall we call this? Let's call this h, and let's call this hi. So this is the hash value of the original sequence y, right? So original sequence y, and this will be the hash value of the sequence obtained from the sequence x by restricting it from xi all the way to xi plus m. So let's write down for both of them what they are equal. So the first, or maybe it would be because of the picture, it would be better to say idea compute pi plus 1 mod q, which would be hi plus 1 from pi mod q, which would be hi. So let's just write down what hi is. So here it is. So hi equals to the following quantity. So it is xi plus 1 times d to the n minus 1 plus xi plus 2 d to the n minus 2 plus all the way to, sorry, it's f of xi. So we map the symbol into its numerical value. Right, what does f do? If this is sign, say, sigma k, this value f of sigma k will be just k, right? So whatever is the symbol, it will just produce its index, and because the alphabet has only d many elements, this can always be taken to be between 0 and d minus 1 all the way to f of x I plus m. And then the whole thing, right, mod p, mod q. Now, what is hi plus 1? Well, in hi plus 1, we drop this guy and start with that guy, right? So this will be f of x I plus 2 d to the m minus 1 plus f of x I plus 3 d to the n minus 2 plus now this guy will be f of x I plus m times d, and finally f of x I plus m plus 1. Right? Simply, if you look at the new sequence, the largest digit of on the largest position digit of the new sequence is the second digit of this sequence. So it will be this times d to the n minus 1, and then as you go at the very end here, rather than being the free term, variable free term, without any power of d or power d to 0, this will be with power d, and 0 terms d to the 0, so this will be d to the 1, and d to the 0 will be this term, right? And that precisely corresponds to this, and then the whole thing mod q. Are you with me? Okay. Are you?
Yes. No.
So it's very simple. So what do? We replace the symbols here with their indices. They can be seen as digits of a number in base d, because there are only d many different of them. Now, if you see them as digits, right, then this is the one with the highest power, which is m minus 1, right? If we have m digits, the largest power is m minus 1, and the smallest power is just d to the 0, right? Now, how can I efficiently get hi plus 1 from just hi? Yes?
I don't get why there's only d digits.
Okay, we assume that our alphabet consists of d many different symbols.
Okay.
All right?
Okay. I forgot that bit.
So we assume that, if, for example, if these are just decimal numbers, it will be just 10 digits from 0 to 9. If this is DNA, there will be just 4 letters, right? So if it's D is 10, if they are decimal digits, in case of DNA, this will be just 4, right? And you simply see the sequence of indices of the symbols as digits in that base D. What does this mean? Well, this means precisely this. Right? Since I have all of these guys are between 0 and smaller or equal than d minus 1, right? So they are really digits in the base D. How can I get hi plus 1 efficiently from hi? Somehow I have to massage this into that. What do I have to do first of all? What shall we do with this guy?
Replace I plus 1.
Exactly. We want to get rid of this guy. So how did I call this P, right? I call this PI. Right, so I will simply take PI minus D to the minus f of x I plus 1 times d to the m minus 1. And what is then this? Well, this will be precisely the sequence f of x I plus 1 times d to the m minus 2 plus all the way plus f of x I plus n.
Should be
It should be two.
I plus 2 for the first term after the equal sign.
Oh yes, sorry. I plus 2. Okay. So this gets rid of this digit. So to get this, what do I have to do with this?
Times D.
Exactly, times d. So now we have that d times pi minus f of x I plus 1 d to the m minus 1, and then close bracket, right, will be then just this f of x I plus 2 d to the m minus 1 now, right, the power goes up for 1, plus all the way f of x and I plus m times d. So we are getting there. So this now matches this part here. What is the only thing missing?
Plus X.
Exactly, plus f of x and I plus m plus 1. So this means that d times pi minus f of x I plus 1 times d to the n minus 1 plus f of x I plus m plus 1. This quantity will be precisely my value pi plus 1. Right? So now, because I want to take that modulo q, right? We simply have, now what do we use? That modulus goes through, it's a homomorphism, right? It goes through the addition and multiplication, right? If you take a product of two numbers and find mod q, that will be the same as if you first found mod q of the two numbers, multiply them, and then maybe, if necessary, because it can exceed p, mod it once again with q. So I can take mod of both sides, and I can enter into this, so then I will have here d mod q. Now this, how big is this likely to be? Well, q is a relatively large prime, so maybe I should just write this. You see, d is the number of different symbols. So d is small and q is a large prime. So d, I can just say d mod q is just d. What is pi mod q? That's exactly, so pi mod q is just hi, right? Now this is between 0 and d, so this does not change, so f of x I plus 1 mod Q is just f of x I plus 1. And what, now we have to compute d to the n minus 1 mod q, and this is where the main saving comes. So let d to the power m minus 1 mod q be equal to, how shall we denote it, some c. Okay, so this is, c is much smaller than d to the power m, because m is the number of symbols here, and that can be quite large. So number of symbols times to the power m can be quite large, and when we mod it with q, it will collapse to something much smaller. So then we have, having this in mind, we have that d times hi, right, minus f of x I plus 1. Instead of d to the n minus 1, I can replace it with c times c, right? And then the whole thing plus, of course, the last element is also small, so f of x I plus m plus 1 is equal, and if I node out this by q, I get simply hi plus 1. So, now you can see what we simply have to do. We know now that this is between 0 and d minus 1. We know that this is smaller than q. So how large should q be? Well, simply q times d should fit into a register. Right? So this actually tells you how big you can do. You want to take q as large as possible, so that the possibility of collision in your table is as small as possible, because you will have q many q many slots in the table. So you want q to be as large as possible, but so that when you multiply it with I guess with d minus 1, this should fit into a single register. So now, how do we then compute hi plus 1? Notice, you simply take the previous value, the previous hash value, you subtract this, multiplied by d, and you simply add this. So this is really an extremely efficient, extremely fast way to compute hi plus 1 from hi. So you see, essentially this is just a recursive hashing in which the hash value of the next string is obtained with the hash value from the hash value of the previous string through this formula, right? Which is really, really a very simple and efficient way of computing the next hash value. So then what do you compare? If hi plus 1 is equal to h, what is h? H we denoted to be simply the value, so h is simply p mod q, right? The hash value of the string that we are looking for. I guess I had it, I erased it, okay? So if, which is just p mod if this is equal, then you do symbol by symbol comparison, right? But if your hash table is large, if Q is a very large prime, just the largest possible so that Q times D still sits in a register, then the probability that you have false positives will be small, because the hash table is large and two different strings are, if they were random equal strings, equally likely. The probability to have a collision would be just 1 over Q, so very small. And then you do symbol by symbol checking, but only if the hash value matches. Okay, do you understand everything, how this works? So simply, if you have a sequence of symbols, you replace each symbol with its index. And if you have D symbols, you will have all numbers between 0 to D minus 1. They can be seen as digits in the base D. So any sequence of n many symbols can be represented by this value. And originally, the idea would be to compare this value for the small string with the value of this for a substring here. But of course, this is very large, right? In principle, can be very large. So the idea now is to replace this value with its value mod a large prime Q. And so, in this way, because of this relationship between hi plus 1, between the string and the shifted string, right, that they can be obtained by removing the highest order digit, multiplying by D, and adding the last digit, and then modding out everything by Q. Then we see that the computation of hi plus 1 can be done